Thanks. I'll begin. Heavenly Father, we thank you for this morning, afternoon, whatever this is. And we just thank you for this opportunity we have just to meet and study your creation. I pray that you'd help us to use this time wisely. The students will be able to prepare for the test tomorrow. Oh, wait a minute. Wednesday, yes. And I just say to have a good July 4th in between that, Lord. And I pray. Amen. So here's the course planner, as you know. You may recall fun with matrices. And then we did how to solve systems with eigenvalues and eigenvectors, right? And we saw real and complex eigenvectors. We saw how to use the matrix exponential when there's not enough eigenvectors, right? Talked a little bit about energy analysis. That was the potential energy diagrams we looked at, right? And then we also talked about how to solve non-homogeneous systems. I solved like one of them. Likelihood of that being on the test is pretty slight. I mean, it's just, to me, it's not a very interesting test question. We haven't done a lot of them. There's plenty for me to test before I get to the non-homogeneous problem. Then, of course, the Laplace transform technique is a little bit more fresh for you guys. How to take a differential equation, transform it to the S domain, and then take the inverse transform to go back. We need to know partial fractions. We need to know convolution. Of course, you need to know some trigonometry in case I do something like, hey, take the Laplace transform of cosine 3t times sine t, right? You should be able to deal with that kind of thing. And then more recently, we've been talking about series solutions, the Cauchy-Euler problem, and then, of course, last but not least, the Frobenius method. Now, I don't think the Frobenius method will appear on your in-class test. I think I've tested it enough in the quiz. So I'll focus on series solutions and possibly the Cauchy-Euler problem. So, that's a little bit disingenuous because the Cauchy-Euler problem is the most basic Frobenius problem. So by testing Cauchy-Euler, I am testing Frobenius, and truth be told. And that's your test upcoming Wednesday. As you can see, I adjusted the dates. And so that's what we're hopefully going to talk a little bit more about these topics today for about the first 40 minutes or so. We'll take a break, and then we'll dive right into Fourier series and the heat equation, which will be tested on in your PD project, which is due Saturday. Sorry, I didn't fix that yet. Before 11. And so your test 2 would not obviously be on Fourier series and the heat equation. Your final exam would not cover Fourier series, the heat equation, the wave equation. But it would possibly cover everything before then, excluding, of course, the Frobenius because of what I just said. But any questions?
So the final exam is just going to cover everything up through test 2 and nothing after test 2?
Yeah. At least the summer. In the regular semester, I might test a little bit on PDs. I never test more than about 7% on PDs in the final, but yeah. All right, so if I can, just a second, to protect the innocent. There's no telling what's in my inbox when I go click on it, All right, we're back. All right, so here is the quiz 3 you guys just got done doing. Is there anything you'd like me to focus on as I talk about it? Or somebody to go through it problem by problem? I mean, just go through problem by problem? Okay. So problem 1 and 2 were intended, because about half of you are really not solid on this idea yet, and it's really important that you get this down 100% for the final. You don't want to miss points on this thing, because it's really easy to do that. Now here, you notice I didn't say to solve it, I just said to set up the minimal particular solution, right? So setting it up just requires me to basically figure out, what's an annihilator for this, what's my differential operator that defines the differential equation, in this case d squared plus 4. That gives me cosine and sine as homogeneous solutions. To kill this, I also need d squared plus 4 to kill the cosine 2t, and I need d squared to kill the t times a constant. So this would be my annihilator. I annihilate both sides of the differential equation. It kills off the inhomogeneous term, leaves me with this homogeneous, let's see here, 6th order problem. And so there's the general solution by our usual technique. And I look at it and I go, aha, well, I know this already. That's the homogeneous solution, right? So whatever's not the homogeneous solution, according to our general theorem, whatever's left over has to be a proper template for the particular solution. And then, just as a point of good habits, I changed the C3, C4, C5, and C6 into A, B, C, D, because if I was to go past this point and actually calculate values for the coefficients, the undetermined coefficients, then I'd really want to not work with numbered coefficients, right? I mean, A, B, C, D are way easy to do algebra in. But that's it, right? Now, if you actually found values for A, B, C, and D, well, good for you, but that's not what I asked. So bad for you, because that means that you're not understanding the words that are coming out of my mouth, which is not good. Because then on the final, you might try to do that much harder problem of finding A, B, C, D, which would not be good, right? Because it's much easier to set up the particular solution as opposed to, finding it. I usually have something like in bold caps, do not attempt to solve for the undetermined coefficients in the problem statement to try to ward off that misapplication of effort. But anyway, other important feature here, I got a t over here. That was a dead giveaway that this is a differential equation in time, or at least independent variable t. So my particular solution should also be in terms of t. In contrast, problem 2 was in terms of x, right? Which means that my particular solution should be in terms of x as a general point of notation. This one here, this is really d plus 1 squared in disguise, right? So the homogeneous solution has c1 e to the minus x plus c2 x e to the minus x. More to the point, it's got e to the minus x and x e to the minus x as fundamental solutions. Now, so on the other hand, I have to look at the inhomogeneous term, what I'm calling g, and I have to figure out what will annihilate this. Well, the natural enemy of e to the x is just d minus 1, one of our initial lemmas, and x squared we can kill with a d cubed, right? So the annihilator I would use here would be d cubed times d minus 1. I annihilate the differential equation, and it leads me to the sixth order problem, just a quirk of my pair of examples. And so then again, I look at the general solution which results. I got one piece, which is this. I identify it. Wait a minute, that's my homogeneous solution, so that's not part of the particular solution, right? Not part of the minimal particular solution. If I plug this into the differential equation, it just spits out 0. There's no way it can produce the g. On the other hand, this over here is going to be my template. So I do ax squared e minus x plus b plus cx plus dx squared. As I recall from test 1, about half of you are really, really shaky on this, right? And it affects later problems. Like even if it's not just the setup problem, if it's the work it out problem, if you start with the wrong particular solution, you're not going to be successful, right? I mean, what happens if you start with the wrong particular solution? The algebra leads you to basically 0 equals 1 if you just face it, right? So, once you get to that 0 equals 1 point, you got to ask yourself a question like, did I do the algebra wrong? Is my setup wrong, right? And so that's a much more difficult decision to make at that point. Like, where did I go wrong? That's a hard thing to answer in the middle of a test. So it's so much easier if you just have the right particular solution in your mind, right? So it's important, really, really important to fix this. Okay, back to test 2. So cosine squared t sine t. So the cosine squared is 1/2 1 plus cosine 2t, right? Now, this could be something more, interesting, like cosine 3t times sine 2t or something like that. We spent about an hour on trigonometry in here, right? So that's an homage to that part of the discussion. But of course, this, from Calc 2 is just that. Or maybe you know from trigonometry. I don't know where you know from, but you should know this. Right? Cosine squared is 1/2 1 plus cosine 2t, which is nice because the 1/2 I can pull out. The 1 Laplace transforms to 1 over s. The cosine 2t Laplace transforms to s over s squared plus 4. On the other hand, multiplication by t amounts to minus the derivative in s. And then we take the Laplace transform or whatever's right there next to it. So I have to take dds of 1 over s squared plus 1 because that's the Laplace transform of sine t. And differentiating that gives me 2s divided by s squared plus 1 squared. And there's a minus, so that cancels to give me a plus. Yeah. Any questions? Now, if you tried to think about this all at once, as just like one thing together, well, that would have been wrong. I mean, not productive. Yeah. All right, next. Y prime prime plus 4y prime plus 4y equals this difference of unit step functions. All right, and I give us initial conditions which were 0. So we take the Laplace transform of the differential equation. You get s squared y plus 4sy plus 4 big Y. This is e to the minus pi s over s. This is e to the minus 2 pi s over s by our theorems. And there's no other, there would be extra terms on the left-hand side if these were non-zero, right? But thankfully, I didn't do that to you. So then we solve for big Y. And we basically get the same coefficient function in front of both of the exponentials, right? So in order to go past this point, I have to do the partial fractions on the coefficient functions of s in order to be able to take the inverse transform of them. Here's the partial fractions for you. A over s, b over s plus 2, c over s plus 2 squared, multiplied by the denominator. I plug in 0 and minus 2. Those are natural, right? Those immediately reveal to me 1/4 for a and minus 1/2 for c. S equals 1. Where'd that come from? Yeah, I just picked it. It's just an easy value. What would have been easier? What would have been even lazier? I was thinking about it after I wrote this down. I should have put minus 1, right? If I put minus 1, then it's like 1 plus a, you know, plus b minus c. So that immediately gives you that, you know, b is, I mean, there's no, you end up with no division if you just do minus 1. It doesn't matter. You can put any number you want. Just don't put 0 or minus 2 because you already used those up. Or you could equate, I mean, there's tons of different ways to do this. I don't care how you do the algebra. I just need you to be able to do the algebra, you know? All right, so long story short, here's the partial fractions decomposition of that function. That's I'm calling that big F of s just for the sake of discussion. Then we had a theorem, said to take the inverse transform, right? Well, first of all, the inverse transform of the f is this, 1/4 minus 1/2 e to the minus 2t plus t e to the minus 2t. And then I use the theorem. See, because, I can't get all, I'm sorry, I gotta make it smaller here. So let's see here. Up here, I'm trying to take the inverse transform of that, right? So basically the theorem says you do the inverse transform of whatever that is, evaluated at t minus pi. So I take this right here and I evaluate at t minus pi. See, everywhere there's t, I replace with t minus pi. T minus pi, minus 2, t minus pi, right? All of that gets multiplied by u t minus pi. That's the theorem. And then I do the same for the other term, but with t minus 2 pi. So 1/2 e to the minus 2, t minus 2 pi, plus I replace t with t minus 2 pi, e to the minus 2 times t minus 2 pi, u t minus 2. And there you go. Now, I don't know, I guess you can multiply it out. You could maybe do some other simplifications, but for my taste, like, that's a perfectly good answer for the purposes of this quiz. Or if this was a problem on the test, this would be where I'd want you to stop. Yeah. Any questions before I go on number 5? We'll just jump in if you got questions. I told you guys direct delta functions are easier. Here's proof. So y prime prime plus y, delta of t minus 2 pi. I even put in non-trivial initial conditions. Hooray! So y of 0 is 2, y prime of 0 is minus 5. So we get s squared minus 2 times y of 0 minus y prime of 0, which is a plus 5 because there's a minus 5 there, plus y. And then the Laplace transform of the delta function is just e to the minus s pi over 2. Then I solve for big Y by doing, the usual algebra. And it gives me this. Now this piece right here, well, that just inverse Laplace transforms to twice cosine 2t minus 5 sine t. On the other hand, this over here I have to use the theorem for. The Laplace transform, inverse Laplace transform of that is sine t, right? But it's being multiplied by this exponential, so I have to shift t to t minus pi over 2, and then multiply by u of t minus pi over 2. Now this, of course, could be simplified to like what? What's sine of t minus pi over 2? You could use the adding angles formula, right? Like that's sine of t cosine of minus pi over 2 minus cosine of t sine of pi over 2. So I believe that this is just minus cosine. You could rewrite this as this minus, 2 cosine t minus 5 sine t minus 2 cosine t times that, right? And then if you wanted to write it as a case-wise defined function, what you'd have would be 2 cosine t minus 5 sine t for t less than 2 pi. And then this would cancel with that for t greater than 2 pi. So as a case-wise defined function, it's these two things to start with, and then it's just minus 5 sine t after pi over 2. Again, I don't really care. I mean, you could, it has kind of a nice breakdown if you actually go into cases, but I think this is a good formula for it too. Logically equivalent. Problem 39, this is an important sort of trick, which is nice to know about. You know, I don't know, maybe you take a standardized test at some point with Laplace transforms or something. I don't know, maybe there's an engineer's exam. Do you have an engineer's exam where you actually do Laplace transforms fast? No? Sadness. Well, this would be useful for that. But it's also just kind of a neat trick. So to calculate the A, B, and C, what you can do, as long as they're not repeated, you can just like take the limit as s goes to 0, and basically just take the f of s and you multiply by s. Those cancel, and whatever's left over you evaluate. That gives you the values of the coefficients. So that's what's in number 38. And so to actually work it out here, it gives you these values, which is, again, just revealing it's just another way to do partial fractions is all it is. If you look at this for a while, it also explains why it's okay to plug in the values of the roots to do the algebra. Because if you really think about it, it's a little bit sketchy what we do, right? We've got this partial fractions decomposition, a over, this, b over that, c over that. And if you look at the this or the that in the denominator, wherever those are not defined is where we plug in to do the algebra, right? But that's weird, right? Because usually it's very sketchy, right? We're like taking the thing which is maximally undefined, the product of all the denominators. And we're multiplying the whole thing by that, which is going to be undefined at the places where the denominators are undefined. And then we plug in those values, and yet somehow it works. There's so much badness in terms of thinking about domain. If you think about the algebra we do for partial fractions, well, if you really want to get into it, you could show that those steps make sense because they really follow from limiting calculations like these. Anyway, really a comment for a different course, so I'll shut up about that. All right, find an integral solution of this guy, y prime prime plus 3 over prime plus 2y equal to g, and we're given symbolic initial conditions. Y of 0 is a, and y prime of 0 is b. All right, so really not different than the problems we just did. We just have to have an a and b floating around. So we have s squared y minus as minus b, because those are initial position and velocity, if you will. And then plus 3 times sy minus a, because again, a is the y of 0. And then of course, I've still got my 2y, so that Laplace transforms to big 2y. Laplace transform of little g is big G. Then I solve for big Y, right? Which gives me this guy, as plus b plus 3a over s squared plus 3s plus 2, and then plus 1 over s squared plus 3s plus 2, right? I thought about it for a second, and I realized if I could figure out the partial fractions for this term right here, then it would automatically tell me the partial fractions for the other piece, right? Because if you think about it, this is a special case of that. With what? With b equals to 1 and a equals to 0. You see, so if I figure out the partial fractions for the first term, I've automatically figured out the partial fractions for the second term as a special case. Now, if you didn't do it that way, it's fine. Like, you can just do the partial fractions for this on its lonesome, and you'll get the same thing. That's cool. I'm just being lazy. So anyway, focusing on this piece here, multiply by a denominator, it gives me that. I plug in minus 2, I plug in minus 1. It gives me this equation and that equation, which gives me that b is minus a minus b, and a is 2a plus b, right? Now, a and b are arbitrary but given constants, so that's as far as I can go. And so this is the partial fractions decomposition of this rational function in S. And on the other hand, if I set a equals 0, b equal to 1, I get this guy is just partial fractions to that, right? And so then to find the solution, I take the inverse transform of this, which is straightforward and given the algebra of star and star star. First of all, the piece without the g just transforms to 2a plus b e to the minus t, that's the a term, minus a plus b times e to the minus 2t, that's the b, right? And then over here, we have integral from 0 to t, g of t minus v, e to the minus v minus e to the minus 2v, because this is the inverse transform of that evaluated at g. So what I'm doing is I'm using the convolution of g of t and the inverse transform of this guy, which happens to be e to the minus t minus 2 e to the minus 2t. So there would be, that's the integral solution. That's best I can do, at least, without being given a specific form for g. That's kind of where we're stuck. Yeah. Yep. So. And that one's a little bit tougher because it involves algebra, right? I mean, it's, yeah. Okay, so now we move on to the wild world of power series. This is kind of like one we did in class, but a little bit easier, I would say. Like one I did in class had what, a cube here and a plus. So it ended up, it was alternating plus minus, plus minus, plus minus when we get into the details of it. This one's a little bit nicer in that regard. So I look at it, y prime prime minus x squared y. So I've got, here's my second derivative. Here's my, I multiply by x squared, so that puts n plus 2. So I meet in the middle, I make n minus 2 bj, I make n plus 2 bj, which converts the n times n minus 1 to a j plus 1 times j plus 2 over here. You know, whenever you're doing calculations like this, something I do to make sure that I'm on the level is if in the initial expression I have this coefficient right here is matching that, it must still be true after a substitution, right? So after I make the substitution, I got a j plus 2 here, and I got a j plus 2 here. Well, that's reassuring, because that's the pattern which I had up here as well. You know, something to look for. Over here, this, I had a sub n, of n plus 2. Here I have, well, it's harder to see. I guess this is two more over here. I guess pattern's a little bit harder to see there, but anyway. Now, this one starts at x squared, right? But the y prime prime has a constant and has an x term. So there's these exceptional j equals 0 and 1 terms from the left sum. In particular, I get 2a2 plus 6a3x. And then I've got some j equals 2 to infinity of these guys. So this gives me two relations. The one thing it gives me is that a2 is 0 and a3 is 0. The other thing it gives me is that there's a recursive relation that we can cipher from this, namely that a sub j plus 2 is equal to a sub j minus 2 divided by j plus 2 times j plus 1. This equation gives me no joy, so I convert it to n instead. A sub n is a sub n minus 4 times n minus 1. Remember the pattern. Whatever's here is there, so that should be n and n, j plus 2 and j plus 2. You know, it gives me a little bit of reassurance that I did the math right there. And then, of course, this makes sense for n equals 4, 5, 6, 7, da da da. Whereas the original one made sense for j equals 2, 3, 4, da da da, which is, again, it's coming from up here. You know, the ultimate truth being that if they have a power series set equal to 0, all of the coefficients in the power series must separately vanish. That's the underlying logic here. And then, so I look at this. This says that there's some sort of fourplicity to the problem, so to speak. I mean, there's a link between n and n plus 4 and n minus 4. You know, so to me that tells me from my really, and maybe this wouldn't be immediately obvious if it wasn't for the fact we worked examples in class and things. You know, maybe this deserves a couple sentences of analysis in a world where you're explaining this to your boss and your boss hasn't seen it lately. Like maybe there's a couple of extra sentences that belong here, but because of our common shared experience, I think it becomes obvious then that a sub 2 equal to 0 implies that a sub 4k plus 2 equal to 0. In other words, like 6, 10, 14, 18, all these guys, all 0. Because once one of them is 0, the whole chain is 0. And likewise, a sub 3 equal to 0 implies that a4k plus 3 is equal to 0 using star. On the other hand, we can look at a sub 4 or a sub 5. Those relate to a sub 0 or a sub 1. And up the chain, 8 and 9, 12 and 13. And we can always go back to a sub naught for this first, you know, multiples of 4. And we can always go back to a sub 1 for multiples of 4 plus 1. And so, putting it all together, the pattern is that. We have the sum a sub naught times the sum k equals 0 to infinity, 4k times 4k minus 1, all the way down to 8 times 7 times 4 times 3, x to the 4k, and then a sub 1, 4k plus 1 times 4k, da da da, times 9 times 8 times 5 times 4 times x to the 4k plus 1. Now, you might have been able to find some pattern in the coefficients and like simplify it a little bit more than me. Totally possible if you did. I'll try to check your work. I guess I get paid for it, so yeah. Anyway, I hope you got this. I don't think it was an impossible problem, but these are always tough, I think. Any questions or concerns, conundrums? No? All right, this one here gives me fits because, well, this always catches me off guard. The stupid example in the book starts with the W and then goes to Y, whereas the problem starts you with Y, but I go to W. So it's kind of notationally flip-flopped from example 3. I hope you could get past that. I know if I'm not sleepy and I'm not paying attention and I keep looking back at the problem and then the example and I don't realize that they have different notations, then it will make my mind tie in knots, which can only be untied with coffee or sleep. But anyway, so that said, the problem we're given, right, is y prime prime minus y equals to t minus 2. If we make a substitution of w of t is y of t plus 2, noting that the derivatives match up because the chain rule of t plus 2 is just 1 again, you know. Then this gives us y prime prime of t plus 2 minus y of t plus 2. And then if we have these at t plus 2, then we have to replace t with t plus 2, right? But t plus 2 minus 2 is just t again. So in the w notation, we have w prime prime of t minus w of t equals to t. And the y initial conditions convert to w of 0 is 3 and w prime of 0 is 0. So once I've got it all over to w, I can take the Laplace transform, solve for w, do some partial fractioning, get that. I have not showed you the details of the partial fractions here because at this point in the quiz solution writing, I got bored of partial fractions. So sorry, but you know this will happen. You are not allowed to get bored of partial fractions. You must show me the details. Okay. I say that, but there are certain partial fractions problems which are so simple that you could literally guess them and check them in your head. It's possible, but to be safe, you really should write down algebra steps for partial fractions because I can't give you partial credits for what you do in your head. You know, there's that, but anyway. So here's the partial fractions. Then you take the inverse transform of that. That inverse Laplace transforms to minus t. Here you got e to the minus t. Here you got a 2e to the t. This is y of t plus 2. We're not interested in y of t plus 2. We want y of t. So then we have to trade our t for what? Y of t is y of t minus 2 plus 2, right? So I replace these t's with t minus 2's. And so that gives me like minus t plus 2 because minus t minus 2 is minus t plus 2. Minus distributing. And then again, minus t minus 2 plus 2 e to the t minus 2. And whenever you do a problem like this with these kinds of substitutions, good check at the end to plug in the initial data. Right? What are we supposed to have? We're supposed to have that y of 2 is 3. Does it actually play out? What happens when you plug t equals 2 into my final answer? Ignoring, of course, the fact that this is an odd problem, so you've already looked up the answer in the back of the book. But or in the freely available PDF of all the problems, which is on the first page of the Google search from the 7th edition of the text, which is probably explaining why the grader for Dr. Wang's class is cursing you guys for just copying answers down. But it's true. Like a lot of you guys in the regular semester, you know, Dr. Wang assigns a couple hundred problems, and what do? You look up PDF in the Google and copy the solution down, which is sometimes not even a real solution, right? It's just the answer half the time. But people think that this will make them somehow learn differential equations. It is most confusing to me, and yet it is most common. But I happen to know the grader on occasion, you know, over the years, and it always confounds them. They're like, "You see what these students do?" Blah blah blah. I'm like, yes, it's not surprising. You have, you know, it's a question of priority, right? Like, maybe you had a girlfriend, or I don't know, you just took up bowling. I don't know. It could be so many different things distracting you from differential equations homework. Not you guys, of course, but I mean, I have tried to safeguard you from that by giving you problems that I just made up. At least some, right? Anyway, enough of that. I'm sorry, guys. So if you plug in t equals to 2, you get 0 from this, right? This becomes 1, and that becomes 2. 1 plus 2, 3. Yay. And if you differentiate this, this gives you minus 1 minus e to the minus t minus 2 plus 2e to the t minus 2. If you plug in t equals to 2, you get minus 1 plus 2, which is 0. Yeah. So it checks. Ignoring, of course, the case. I mean, odd problem. I know. It checks. Here's the, of all the problems to make worth double, the easiest one, right? It's kind of funny. I'm just kidding. It's not worth double. I'm just giving you guys the other one for free. So you deserve a break. Celebration of July 4th. This is free. That's here. So yeah, to convert that to x to the k, we just simply make a n plus 3 equals k substitution, which means the n doesn't, k starts at 4 if n starts at 1, right? And a sub n is going to be k minus 3, so I have a sub k minus 3 over k, x to the k. Yeah. The point of this problem, and the point of all those problems, is a warm-up, right? I really should have put this problem earlier in the homework, right? I should have put this before the y prime prime minus xy equals to 0. That would have been more logical. Sorry about that. But on the flip side, in my defense, I really don't think this is all you should do, right? Like the quizzes I'm giving you guys, these are not sufficient to get up to speed for the test, right? You need to do a few hundred problems from the recommended homework in addition to these over the totality of the course, right? And it's just the truth. But I don't want to make you write those all out carefully and turn them in either, right? So I'm leaving it to you to have the freedom to work the ones you should and so forth. And your book does have several thousand problems, so there you go, right? All right, finally, number 12. This one's kind of a bear. X squared minus x plus 1, y prime prime minus y equals 0. These initial conditions. All right, so this is a power series problem, right? So we can immediately read off the meaning of the coefficient. This tells me that my a sub naught will be 0. This tells me that my a sub 1 will be 1 by Taylor series. All right, so y equals x plus a2x squared plus a3x cubed plus a4x to the 4th. I have that right off the bat using my initial conditions. Now, there's no harm, there's no foul if you do a naught plus a1x and work it out symbolically, and then at the end, put in that a sub, y of 0 is 0, y prime of 0 is 1 rather, which will give you then that a sub naught is 0 and that a sub 1 is 1, right? But it's so much easier when you have initial conditions in this kind of problem to put the initial conditions in at the start, right? Because everywhere there was going to be a sub naught, there's now just nothing, right? So there's less lifting to do in the calculation if we do it like that. Anyway, so here it is, y prime, prime, prime. There was just 2 primes, not prime, prime, prime. And plug it in all of its glory. There it is. And then just start collecting terms by term. Constants, I got 2a minus 1 equal to 0, which gives me that a2 is 1/2. From x, let's see where the x is coming from. I've got this times that, which gives me the minus 2a2, right? But I've also got 1 times that, which gives me plus 6a3, right? This times that gives me the plus 6a3. And then this minus 2a2 is coming from that term, right? Anything else now down here, I've got this lonesome minus x, which gives me the minus 1. All right, so I got 6a3 is 1 plus 4a2, but a2 is, what is it? It's a half, right? So this is 1 plus 2, which is 3. 3 over 6 is a half. So a3 is a half. X squared. So x squared, we have x squared times 2a2, which gives me the 2a2. We have minus x times 6a3, which gives me the minus 6a3. We have the 1 times the 12a4, which gives me the 12a4. And then over here, I get a minus 3a2. And then from down here, I get the minus a2. So solving that for 12a4 gives me this, which tells me the a4 is minus 9a3 minus a2 over 12, which is 9 halves minus 1/2, using the ones up here, divided by 12, also known as 4 divided by 12, aka 1/3. Okay, I'm only supposed to find the first 4 terms. I've got up through a4. I'm definitely good to go. So here we go. we have x plus 1/2 x squared plus 1/2 x cubed plus 1/3 x to the fourth plus dot, 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 dot. So I forgot if I checked my answer on this or not. Is this what you guys got? Yeah? Okay. Problem 13. So what we got to do is figure out what the singular points are to figure out what the minimum radius of convergence is. So to do that, I have to complete the square on this guy. Wherever that's 0, that's going to give me a singular point. Let's see here. Because, of course, if you solve for y prime prime, you'd have like y prime prime minus 3 divided by that quadratic times y equal to 0. And if you go back to our definition of singular point, that wherever the coefficient of the y function is not defined would be a singular point, essentially. But it's also true equivalently that if you have a coefficient function for y prime prime, if that's 0, it's going to give you a singular point, right? So I just think in that way. So anyway, when is this going to be 0? Well, complete the square, if I did it right. X plus 1/2 squared. I had a 1 here, which is 1/4 plus 3/4, right? So there we go. So my singularities are at minus 1/2 plus or minus I root 3 over 2. So that's roughly, that's not a word, roughly here and here, yeah? And we're saying that the center is at 1. So what's the distance from there to there? Well, it's made from the right triangle, where the base of it is 3/2 distance and the height is root 3 over 2, right? So that distance is the square root of the sums of the squares of those guys, also known as 9 plus 3 over 4, aka 12/4, which is 3. So root 3 is the radius of convergence there. Now, I didn't write it down, but what would the minimal interval, open interval of convergence be there? I didn't ask for it, but sometimes I do ask for it. So what would I have, what would the interval of convergence be here? So 1 minus the root 3, 1 plus root 3? Yeah. Very good. We can expect that the solution, if we were to find it to that problem, would converge at least that far. What happens at the endpoints? Anybody's game. You can guess, but yeah. Okay, then a pair of Cauchy-Euler problems. These are, this is kind of like a vacation after the earlier problems, right? If you get the idea here, we just look at r times r minus 1 plus 6r plus 6, basically coming from plugging that in when we twice differentiate, we pull out r times r minus 1. We differentiate once, we just pull down an r. And there's an x to the r that's factored out, so the coefficient has to be 0. This is the so-called, I think we call this the characteristic equation here. Anyway, you factor, you get minus 2 or minus 3. There it is. This one, we get r times r minus 1 minus r plus 17, which is r squared minus 2r plus 17. Completing the square reveals a complex root, right? 1 plus or minus 4i. So if we look at z, let's say, equals to x to the 1 plus 4i, that's x times x to the 4i, which is x cosine 4 log x plus I sine 4 log x all times x, right? So pick off the real and imaginary parts of this, and that gives us our standard solution. Now, this business right here, you don't actually have to write out. I'm just explaining to you where this magical formula comes from, right? It's just picking off real and imaginary parts of our complex solution again. And so there it is. So, as a point of order, one of the things you should have on your formula sheet should definitely be, so for a Cauchy-Euler problem, if I have different kinds of roots, these are the solutions, right? What happens if they're repeated? Like, what if I had r equals to 3, r equals to 3 as what my r value worked out to? What would the solution be? C1 x cubed, right, plus C2 x cubed times what? What happens when there's a repeated root? What do we learn? I should make you guys derive it on the test, apparently. The repeated root for constant coefficient, we multiply by t or x, depending on what variable we work on, right? For the Cauchy-Euler problem, when we have repeated root, we multiply by log x, or log t, depending on what the variables we're using, yeah. And I don't think I ever told you what happens if we have a three-peated root in a Cauchy-Euler problem. Like, we have not discussed that. Let's see here. Oh, and then finally, the final problem. So here we have x, y prime prime, plus y prime, minus 4y equals to 0. This is a Frobenius problem. It's a regular singular point. And so here's my Frobenius solution. You know, a naught x to the r plus a1 x to the r plus 1 plus da 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 da. Now, I've mostly been using summation notation, as I will down here. But I'm just trying to find the lowest order terms are these guys. So the indicial equation. I mean, you could jump straight to the indicial equation without writing all this if you just like use the book's formulas properly. I'm fine with that. But one way or the other, we should find that the indicial equation says that r is equal to 0. 2 times. So boring. Sorry. I wish it'd come out to be like a half or something. That would have been so much more exciting, because then it would have been something we couldn't have found in our previous arc of the course, right? But this is one of those Frobenius problems which actually does just produce a power series. Sometimes Frobenius method gives you a power series. Here's one of those cases. Curses. Anyway, with r equals to 0, then I plug it into the, you know, here's my y prime, and then I just have to plug it back up into here and go order by order. Usual song and dance. The difference here, right, is that before you go to the order by order calculation, you have to figure out what the index was, right? Now, I'm telling you this for your informational purposes. As I told you, I'm not testing Frobenius on test 2. So finding the indicial equation for a problem like this is not something I'm going to test you guys on this summer, to be completely frank with you. I very likely will test you on Cauchy-Euler, right? So in that sense, I'm being disingenuous, because the characteristic equation for the Cauchy-Euler problem is the indicial equation there, right? But I'm just making a stupid distinction between these problems. Anyway, for this one, you plug it in order by order. We get, in fact, 4 times the initial constant, 4 times the initial constant, 16/9 times the initial constant, 4/9 times the initial constant, which gives you this beastly answer right there. So not too bad, actually. Any questions? All right. We had quiz 2, right? So one of the things you need to know is how to find critical points, right? Finding critical points is easier than analyzing them, right? Analyzing critical points, that'd be kind of a tough question unless I give you the phase plane plot, right? Although if you've been studying, you know that there's some relation between the eigenvalues, right? Like if all the eigenvalues are negative, it's a stable, like the origins, if we're talking about a linear differential equation, right? If all the eigenvalues are negative, if all the real parts of the eigenvalues are negative, right? That means all the solutions are getting sucked into the origin eventually. So the origin is a stable critical point. If some are negative and one's positive, it's unstable. It's a saddle point, because if any of the eigenvalues are positive, that means there's like an e to the lambda t term which blows up, right? So depending on where you start, you could go off to infinity from the origin. Then, and I'm not sure what to say about, what if one of the eigenvalues is 0? That's, not sure what to say about that offhand, actually. Not sure I know the name for that. So anyway, if I don't know the name for it, probably you don't have to either at this point. In terms of analyzing critical points, though, I think mostly I'm interested in if I either if I give you a p-plane plot for one, you can analyze the type of the critical points, right? And of course you can always, I can ask you to find critical points for a system of differential equations. That's fair game. We've had a few of those. The other thing I could ask you about in terms of stability would be, here's a potential energy function, right? Plot the potential energy diagram, analyze the stability of the critical points. That's something I could ask you without providing a p-plane, because you can create the diagram as we do at the end of this, right? This guy. So here, there are three critical points. This guy, and that guy. These are stable centers, right? And this is an unstable saddle point, because some solutions are flowing into it and some solutions are flowing out of it, right? So this is an unstable saddle. These are stable centers, actually. So this is a, possible thing I might ask you about. So just let's take a step back here. So there's stability and critical points to think about. Obviously, I can't ask you to use p-plane on the test, right? You're like, I don't mind if you let us use our computer on the test. That's fine with me. Right, fine. But let's see here. For a third order problem, to be friendly, I might do something like, if it's a third order problem, I might throw you a bone like, hey, by the way, this vector is really interesting. What's that probably mean you should do? Probably should take that vector, multiply by the matrix, and see which eigenvalue it has, right? Like for this problem, if I was to say, here's a matrix, 1, 2, 2, 2, 0, 3, 2, 2, 2, 3, 0. By the way, the vector 0, minus 1, 1 is interesting. That would tell you what? Now that we've had this talk and you understand my silly way of presenting a problem, if you multiply this by that, then you get minus 3 times that vector, which would show you that the eigenvalue there is an eigenvalue of minus 3, right? Once you know that, that means that when you calculate the characteristic equation, you can definitely factor out the lambda plus 3. So telling you something like that gives you a way out of just the arbitrary cubic factoring problem, right? Factoring an arbitrary cubic without help is difficult in time pressure, yeah? But if you know one linear solution, then you know what you're looking to factor out. Once you've factored one linear thing out of a cubic, then you've got a quadratic left, which you have complete ownership of, right? Like there's no quadratic that can escape your clutches. You own them all. They have no chance to survive. So anyway, that problem seems like a bit much. I mean, that problem too, I would be devoting like half your test question time for that if I asked that one. I mean, it's going to take you guys 25 minutes to do that on a test. Let's see here. I'm wandering here. If I give you a system of two differential equations, if I give you y prime equals to some number times x plus some number times y, and I give you y prime equals some number times x times some number times y, right? How do you solve it? Turn it into a matrix problem. Calculate the characteristic equation, right? If the eigenvalues are real, then they're distinct. That means you got to find what? Your two eigenvectors, then you put together the eigensolution, right? If the eigenvalue is complex, then you find your one complex eigenvector and you pick off the real and imaginary parts. What if I give you initial conditions? I mean, maybe then it makes sense to use Laplace transforms instead, right? You can also take Laplace transforms of a system and solve the algebra that results. That's another way. We did a problem like that. That might be faster if you have initial conditions. So I will tie your hands. There will be problems I'll say use eigenvector, eigenvalue technique to find the general real solution, something like that. But there might be another one where I don't fetter you, so you could use different methods. You could use the eigenvector method, you could use the Laplace transform method, or there's another method, right, which we did very, very passingly, but there's also just the elimination at the level of differential equations method, right? Like we solved x prime equals to minus y prime equals to x by just plugging in one of the differential equations into the other, solving the resulting second order differential equation, and then differentiating to find the second solution. So there are also problems where it just makes more sense to just kind of do substitution. But I do want you to master the eigenvector eigenvalue technique, and I will test on that. That's a promise. Let's see here. You know, like this one. In retrospect, it would probably be a healthy exercise to work this out using Laplace transforms instead, right? What do we got? dx dt is, what is it? Minus 2x minus 2x plus 5y minus 5y. Thank you. And what's dy dt? X plus 2y. And we also know that x of 0 is 1, y of 0, 0. So there's something for you guys to do in the break, is try to work that out with Laplace transforms. See if you can reproduce the solution and see what you think. See if it's easier. Matrix exponential is important. I do want you to understand that. And we've done a few different kind of trick problems with that. You know, sometimes if the matrix has a simple enough pattern when you raise it to a power, then you can just simplify the matrix exponential directly from the definition. We also did things with the magic formula. Important fun facts about the matrix exponential: it's a solution matrix, right? Which means its columns are separately solutions. It's a fundamental matrix, which means it's a solution matrix which is also invertible. So the determinant of the matrix exponential is non-zero, which is nice to know. And you know, so we had this Cayley-Hamilton problem, which is nice. And you know, this is something I try to test on because I spent a lot of time on it. Spent a whole hour on this, right? We take the magic formula, and then we use the eigenvector. It gives us out these either eigensolutions or generalized eigenvector solutions. Now this one's a little bit more complicated because these are actually complex ones, right? So these give me a pair of complex solutions. I picked off the real and imaginary parts to get the corresponding real solutions to this problem. Man, I almost asked this problem earlier in the problem set. I'm sorry, it's kind of redundant in some sense. This is kind of there was a problem very much like this earlier in the problem set. My bad. And then here, this is a good. If I do ask a numerical generalized eigenvector question, it would be like this. I might ask a symbolic one, which was like 2 problems ago, where I just give you some vectors, say they satisfy these relations, put together the solution, right? So I can ask a sort of symbolic question which doesn't require a lot of computation, but requires me to see whether or not you've actually understood what I said about how to use the magic formula to put together the solution from the matrix exponential. You know, there's something I want you to understand. It's definitely not as important as like having down eigenvectors pat. Like you need to know how to find eigenvectors and put together the eigensolutions in the real or complex case. That's important, and I hope you get in there. These are just fun, but anyway. All right, well, let's take a break. I'll try to start again about 12:05. So, and we'll be into the wild world of PDEs and Fourier series. So, about